Morning, Your Honor. Jordan Jaffe for the plaintiff, Waymo. With me today is Mr. Perlson, Mr. Nardinelli, Mr. Corridor.
Welcome to all of you.
Good morning, Your Honor. Arturo Gonzalez from Morrison & Forster on behalf of Uber. Also here is my partner, Michael Jacobs, my partner, Wendy Ray, and the two associates who will be doing the presentation are Esther Kim Chang and Michelle Yang.
Welcome to all of you. Well, we're going to come to that. Can you stay for a while? And okay, good. That's great news to hear. I have some projects in mind for you, but maybe we won't get to that today, but possibly we will. Okay, thank you for coming. All right, so we're here for a tutorial. And let's do this. What did I say, 40 minutes, 45 minutes, 40? So you get to go first, and you get to go second. The floor is yours. Just so the public out there will know, the ground rule for this tutorial is everything has got to be in the public domain. So there's no trade secrets going to be shown today. If that's what you came for, too bad, you won't see anything. But this is to educate the judge on things in the public domain. So there we go. All right, go ahead.
Thank you, Your Honor. Once again, my name is Jordan Jaffe, and I'm going to be presenting this today with my colleague, Mr. Corridor. So before I get started, I wanted to kind of give you a roadmap of where we're going to go today, the topics that we're going to touch, at least with regard to our portion of the tutorial. So the first thing that I'm going to talk about are basic principles of LiDAR. What is LiDAR? How does it work? The basic kind of underlying principles at play. Then we're going to transition into early applications of LiDAR, what it's been used for historically. It's actually, in its most primitive forms, it's actually not that new. It's been around for about 50 or so years. Then we're going to fast forward in time, how it's developed over the past few years. And then we're going to transition to how it's been used in self-driving cars, most relevant to this case. And then continuing on the timeline, we're going to talk about the early self-driving cars, how they use LiDAR, how they use some other sensors that are relevant here. And then lastly, we put together some slides on the two patents that we highlighted in our preliminary injunction motion, speaking about the example and the specification, and we can go through those in as much detail as Your Honor wants at the end.
And while you're pausing, I have a question about the way it's spelled. And I want to make sure there's no trick involved here. How do you spell the generic version of LiDAR?
Sure. So we actually have a slide on this exact point, which is
all right.
LiDAR
and
or
you
LiDAR.
Anticipated me. All right, go ahead. Okay. Is that it?
The short answer is there are two words that essentially describe the same thing. LiDAR would be light detection and ranging. LiDAR would be laser detection and ranging. But laser is a form of light, so we're talking about two forms of the same thing.
Right, but I've noticed that sometimes it's spelled with a small I, and sometimes with everything else capitalized, and sometimes it's just the L is capitalized. And I want to make sure that if I use LiDAR in one way or the other, that one side's not going to come back and say, "Oh, Judge, we thought you were talking about the trademark thing. We didn't know you really meant generic." I don't want to be the victim of that. So I want us to all agree. Right here, Mr. Gonzalez, you need to stand up and let's all agree that You tell me, does L small I DAR mean any and all versions of LiDAR, or does it mean just the Waymo trademarked version?
The answer is yes, any and all.
Any and all. All right, so if I were to give you an interrogatory, which I'm inclined to do, you got to go dig up some information within your company on LiDAR. You're not going to come back to me later and say, oh, we thought you just meant the Waymo version.
Correct.
Okay, all right. That's what, you understand it that way too?
Yes, Your Honor.
All right, so that's good. So my law clerks we're going to use L, small I, capital D, capital A, capital R. That way. Now I'm reserving the right to use any other version too, but if I happen to, I just don't want to be accused of referring to something much more narrower than I intended. All right, go ahead.
So to jump back into this slide, I'm going to start by just talking about the basic underlying principles of LiDAR. And we have a little animation here to help with this, and this is kind of a different kind of detection, sonar.
Echolocation.
So we have our little bat here, which is going to send out sonar, so noise, and you're going to see that it's going to bounce off the small little object on the right-hand side, and the time it takes for those waves to go out and come back is how the bat kind of quote knows how far away the object is. And so it's the calculation of the time that it takes to bounce that we're looking at. So how does this go to LiDAR? So LiDAR is another form of this kind of analysis, but instead of sound waves, we're going to use light. And what we put here on this slide is kind of a definition of what we're talking about in terms of LiDAR or LiDAR with whatever capitalization we may want to use. But the point being is that it's a device consisting of a photon source, that is a light source, as it notes here, frequently but not necessarily a laser, and a photon detection system, that is something that detects light coming back, and a timing circuit. And then we also have some optics to help make this all work. So what are we talking about? How does this work in the LiDAR context specifically? So what we've got here is we've got another little animation, and we're showing that there's a laser on the left-hand side. It shoots out, it hits the object, and comes back. And we're timing how long that takes. So let me just do the animation again here. We can see it takes 100 nanoseconds. And what we do in the little timing circuit on the left-hand side is we're going to ask, okay, I know the time of flight, which is this 100 nanoseconds. I know how long the speed of light is. I can use this formula on the top in order to figure out how far away the object is. So what we've done now is plugged in these numbers, speed of light on the left-hand side, the time of flight that we just accessed, divide by 2, and we now understand that the object is 15 meters away. And then we've added this little annotation that says, a rule of thumb, to put it in a different form, is approximately half a foot per nanosecond. Now, one thing that's going to come up a little bit later that I just want to touch on now is the idea that in our prior slide here, you can see that the laser just goes out and shoots right back. In reality, what we have is we have one laser that comes out, and then it doesn't bounce back like in a science fiction movie. What happens instead is it bounces in all sorts of different directions. And what we've labeled it here is this kind of diffused reflection. And what this means is we need to shoot a lot of lasers out in order to get photons back coming in the second direction. And some of the literature actually talks about when you shoot out 1 million photons, only one will come back in the same direction. So we need to use a lot of photons in order to kind of make this work. Now, taking this a step further, I've depicted here an example of a LiDAR. And I'm going to just walk through each of the pieces. Basically, what we're doing here is we're going another step under the covers and saying, okay, we understand the principles involved. How does it work? So the first thing we're going to talk about is what's called this control and acquisition part. And what we've done here is shown a circuit. This is similar to the timing circuit that we talked about before. This is telling the signal when to go, measuring the time of flight, things like that. So the first thing it's going to do is tell the signal generator, all right, time to generate a signal. And specifically what it's going to do is do a pulse of light. It's going to generate kind of a wave of light in a laser or other light source. Example here I'm going to use is a laser. It's then going to go out through the transmit lens, which we'll talk about in a little bit more detail shortly. But it's going to go out through the transmit lens, which is going to do a couple things. But then it's going to go to a target, assuming there is a target or other object, and it's going to come back. And then it's going to hit this receiver or detector that we've talked about here. And what this is a photodetector. So what this means is it's a piece of semiconductor material that takes photons in and converts those in an equivalent amount or some relationship to an amount of current. So then it can send a signal back to the control and acquisition part and say, okay, I've got some hits. And then it can do that time of flight calculation we talked about before in order to figure out how far away the target is. So I touched a little bit earlier on the two lenses here, just to give a little bit more detail on what they are doing in the example that I talked about before. The top one is going to do two things. It's going to collimate the light, which is project. And the two things it's going to do are project the outgoing beams and make them parallel to one another. So you can see it changes which direction they're going and makes them parallel. On the other side, the receive lens, what it's going to do is it's going to focus the incoming beams on the detector that we talked about earlier. So it's got to aim them in exactly the right spot where the detector is, or that small number of photons, we're going to miss it. And then we're not going to get any range information. Taking a step forward, what we have here is an example of a laser, and what this diagram shows is essentially a laser diode. Now, a laser diode is an example of a laser that's useful for one reason, because it's small. And it's also relatively inexpensive. But some systems get more expensive when they use laser diodes because there's what's called a high divergence. And that's what we marked in red here on the right-hand side, which means that the light kind of sprays out in a cone formation, and it's an unequal cone. It's kind of an elliptical, as it's noted here. So that creates all other sorts of problems that have to be compensated for in the system. So the example LiDAR I was talking about before is what's called a bistatic LiDAR. Now, I'm going to show a second example here. This one's called monostatic. What that means is that there's one lens instead of two, and there's what's called a transmit and receive combiner. And TX and RX in this context means transmit and receive. Now, this design typically talks about a single beam design. And the reason for that is because we have this combiner that includes some kind of specifics in order to make this work, in order to be able to transmit and receive using the same area. And just to give a little bit more detail on an example of how this works, again, in the single beam context, what we have here is a different diagram showing how a single beam monostatic LiDAR works. Again, we're talking about single lens, single beam. So here, what we're showing is on the left-hand side, we have our laser. It goes through what's called a polarizing beam splitter, and then it goes through a couple other things, but in essence, it goes out into the world through the lens. On the reverse side, in terms of reception, it comes back and hits this polarizing beam splitter, and it reflects down to the bottom. Now, just to give a little bit more detail on what is a polarizing beam splitter, how does this work? So in essence, what it is it's a filter that lets light go through one direction. That's the laser on the left. But when light comes back the other direction, it's going to block it and hit it to a mirror that goes on the bottom. Now, it gets difficult here because there's certain optical problems, which we've eliminated from this picture, but there's certain optical problems and degrees of tolerance that become harder in this design versus the bistatic design that we were talking about earlier. So next, we're going to talk about early applications of LiDAR. I'm going to hand it off to my colleague, Mr. Cordova.
All right, thank you.
Thank you, Mr. Jaffe. Hi, I'm Felipe Corredor. I'll be continuing our presentation today. So now that we've covered what the basic principles of LiDAR are, I'd like to discuss what has LiDAR actually been used for. Some of the earliest applications, as you can probably figure out, is just finding the distance to a target. This is called range finding. This was a very widespread application soon after the invention of the laser in the 1960s and 1970s, especially by militaries around the world. Here I'm depicting an example to illustrate that the same time of flight principle that we've been discussing with Mr. Jaffe can apply to longer distances. So for example, in a military application, it might take 10 microseconds for the beam to reach the target, and then using the formula that we saw earlier, you can compute that that translates to 1.5 kilometers distance. Now in the literature, this is sometimes known as single point or zero-dimensional LiDAR because all you're getting, the only information you're getting is the distance to a specific point in the environment, your target. So that's why it's known as 0D LiDAR. What you can do with such a single beam LiDAR is you can actually sweep it across a plane, as will be shown in this slide. And by sweeping the single beam LiDAR across a plane, you can get information about the points lying on that two-dimensional plane. For example, NASA and the U.S. Geological Survey did this in the early 2000s to map out the topography of areas of interest, as depicted here. And what it looks like is there's a neat animation here. It's still the single beam, and you're finding the distance to each point, and as the plane moves forward, this two-dimensional plane where the LiDAR is scanning moves forward and gets you a little bit of a sense of a three-dimensional map of the underlying environment. Now, how does this actually work? This next slide explains how people used to do this in those early days. Basically, you have some kind of mechanical moving part, usually a rotating mirror. And your laser and detector electronics, the components Mr. Jaffe talked about earlier, stay largely stationary. And then as the rotating mirror moves, you're able to scan across the plane, depicted here by the blue semicircle. And you get information about all the points lying on that plane. Now, what does that information look like? That information is called a point cloud. So what you're getting is range information, how far each point that the laser hits is from your LiDAR unit. And as you scan it across a plane, you can figure out how far each point is. So for example, if you have a room here with a blue curved wall and a little green box in the middle, as you sweep the single beam LiDAR system across the plane of the room, you get the following, which is a bunch of points, blue points representing the blue wall, and then where the wall is obstructed by the green object, you see closer points. This is a very important concept for LiDARs, the point cloud, because this is basically what enables a LiDAR to see the environment by making lots of different range calculations to many different points in the environment. So that's how we get to self-driving cars. I mean, LiDAR systems using the point cloud concept are able to see the environment around there, and that enables self-driving cars to not only see the world, but also feed this information, the 3D point cloud, into the computer and run the software and make decisions, get the computer to make decisions for how to drive the car, when to slow down, when to stop, etc. So here's a depiction of an early 3D point cloud from the early 2000s, from the report we submitted to Your Honor, I believe last week. So as you can see, it's a very detailed point cloud. You can make out two very clear cars on a flat road, perhaps a parking lot, under a tree. Now, the main problem with the LiDARs, if you're scanning a three-dimensional environment with a single beam scanning LiDAR, is you need to scan in two directions. So not only are you moving across a plane, but you also have to scan the plane up and down. And this takes a long time. In this paper, they noted that to generate this high quality of a point cloud, you needed to spend several minutes sweeping the LiDAR across the environment. But when you do get the 3D point cloud, this 3D point cloud has a lot of information. So as you may have figured out, each point has at least 4 parameters. 3 of them are the obvious XYZ parameters, which tell you where exactly in the world is this point in relation to your LiDAR unit. And then many LiDAR systems, we have not discussed this yet, but many LiDAR systems also allow you to make a measure of reflectivity. As Mr. Jaffe mentioned, when you shoot out lasers, very few photons actually come back. But different surfaces and different colors can have different reflectivity. So for example, if you're looking at the road surface, there might be white lane markings on a dark pavement. and the white lane markings send more photons back, reflect more photons back, and so that you will be able to see this using the LiDAR system because the detector can measure that there was more photons that actually came back as opposed to dark pavement next to it, which had very few photons coming back. And another neat thing you can do with point clouds is you can actually rotate them and manipulate them. So these 4 parameters are very easy for a computer to manipulate, and it's a very powerful, it's basically an image of the entire world around the car. Now, how would you do this with the single beam scanning LiDARs that we've been discussing? Basically, the single beam LiDARs scan across a plane, which is not good enough for self-driving cars because you need to be able to see short objects. You need to be able to see signs hanging overhead. So what people figured out early on is you'll just take one of these 2D scanning systems and you'll just nod the unit up and down so that you scan the 3D environment around you. Now, this has a big problem in that it takes a long time. It misses a lot of points, so you get very low resolution in the point cloud. And because it takes a long time, the refresh rate is very low. And what the refresh rate is how often does the scenery update? Like this 3D point cloud is what the world looked like several minutes ago versus a few seconds ago. And in a self-driving car, you really want to be able to update the scene several times every second. Now, with those early types of LiDARs, if you mounted them on a moving car and you tried to sweep the 3-dimensional environment around the car, this is what you would get, a very, very low resolution, low quality point cloud that you can't really make out the objects in. For example, maybe you can tell the road is flat in front of the car and that there's like some kind of objects on the sides of the road, but that's about it. It's a far cry from the nice picture we were looking at just a few moments ago. This slide just summarizes the points I've already discussed, which is scanning generates very low quality point clouds because you're scanning a 3-dimensional environment using an inherently 1-dimensional single beam LiDAR. And you need to sweep that in at least 2 directions. And then it takes too much time, leading to low resolution and a low refresh rate. And in addition, there's a very fundamental limitation that you have to understand when you have a single beam is that you have to wait for the laser to hit the target, come back, and then you can sweep. So it's a very mechanical process, and it takes a long time. It's just inherently limited by the fact that you only have one laser and one detector, and you cannot take more than one measurement in parallel. So when the Department of Defense looked at this in the early 2000s, they wanted to make self-driving cars for military applications and combat zones. And they realized that the ongoing research and development programs were actually, they were not good enough. They didn't see anything promising. And so what they did is they instituted what's called the Grand Challenges, which were a contest for anyone who wanted to enter, usually academic institutions or big companies. And the point of these was to try and build a self-driving car in a simplified environment. They used, in the first 2 Grand Challenges, they used a desert course. And in that course, you have 2 main requirements for sensing in the environment. One is sensing, which is mapping out what it looks like. Is there other cars? Are there other cars near you? Is there any obstacle in the way? And you also want to be able to map out the terrain underneath the car so that you can localize the car on a map and figure out where it is and where you want to go if the car is going to drive itself. So in 2004, the first course took place in the Nevada desert, and no team was able to complete the course despite the relatively simple nature of the challenge being in a desert and not too many obstacles around. Now, so the DARPA doubled the reward, and in 2005, the challenge had a $2 million prize, and 5 teams completed the course. The Stanford team won, and the Stanford team was led by Sebastian Thrun, who later went on to found and lead the self-driving car project at Google. Then in 2007, the challenge got a little bit more complicated. They wanted to see if you could figure out a way to run self-driving cars in a simplified urban environment. So they used a closed Air Force base. And in this contest, several teams completed it, and CMU, Carnegie Mellon University, won the race. And that team was led by Chris Ermsen, who also later, after Sebastian Thrun, led the self-driving car project at Google. Now, what did the DARPA contestants learn from these grand challenges? What they figured out is that you needed to use different sensors in combination to be able to get you a view of the world. And so many of the teams would use LiDARs, radars, and cameras together. Now, LiDARs we've been discussing, so we should be familiar with by now. But radars have an inherent disadvantage in that because they use radio waves, the wavelengths are very long, and the resolution is just limited. You can't get a sharper resolution as you can with LiDAR. And cameras, the inherent problem with cameras is that you rely on outside light to take pictures. So if it's night out, if it's dark, if you're under shadows, if the sun's too bright and it's blinding your camera, you can't really see. This is still a developing area, so no one knows what combination of sensors, commercial self-driving cars will have. But not everyone thinks commercial self-driving cars will have LiDAR. For example, Tesla opts not to use LiDARs in their systems. There's a regulatory framework in the context. So DARPA really started a lot of research and development in this area. Eventually, the NHTSA instituted a regulatory framework that really maps out the self-driving car classification from level 1, which is assisted, very simple self-driving tasks. Basically just like follow the car in front of you, adaptive cruise control. And for that, you can use very simple like 1D LiDARs. You don't even need to sweep them perhaps. And then levels 4 and 5 are the most complex. When you talk about self-driving cars, you really are talking about levels 4 and 5, which is no human driver is needed, basically. What did the DARPA teams use in terms of LiDARs? Some of the early commercial systems that the DARPA teams used were Regal and Seek LiDARs. These are 2D scanning LiDARs of the types we've been discussing. But there were also options with the multi-beam scanning LiDAR. So this is an extension of the principle of the single beam scanning LiDARs, but now you have multiple beams, one on top of another, so as to get a better view of the world. For example, in this patent from 1993, you could be able to make out the stop sign by shooting 4 light beams, laser beams added. The main disadvantage, as Mr. Jaffe briefly mentioned, is that doing so really complicates the optics. But it was known that, people had done it in self-driving ranging cars. At the time of the DARPA challenges in the late 2000s, there were commercial systems such as Ibeo's Lux system that could use 4 scanning beams to sweep the environment so as to get a little better 3D sense of what's around the car. One of the teams in the 2005 challenge actually developed their own LiDAR system, which was a 64-beam LiDAR system that had a 360-degree field of view horizontally and a 20-degree vertical field of view. This was Team DAD, which was composed of 2 brothers, David Hall and Bruce Hall. They ended up commercializing this system under the company Velodyne, and this is depicted here. Their system was called the HDL64. This is a good example of how complicated the optics can get when you have a lot of beams. I'll show you an image that's still oversimplified. Basically, the Velodyne system has 2 optical cavities, one on top of each other, and each optical cavity has 3 sets of lenses, 2 transmit lenses on the outside and 2 receive lenses, which are slightly larger in the middle. Now, you shoot outgoing beams from the transmit lenses, and then you receive the incoming reflection in the received lens. And you do that a lot of times. Here we've only depicted it 4 times, but in reality there's 64, there's 16 behind each transmit lens. And this goes on very fast as the whole unit rotates. In 2007, however, at the Urban Challenge, people realized that the Velodyne sensors were pretty good, but they were not good enough for urban driving. And the main problems that people found out was that it had insufficient angular resolution at long ranges, and it was a very unwieldy unit. And how unwieldy is illustrated in the next slide, where we show an 8x8x11 unit that weighs 28 pounds. And this is meant to be mounted on top of the car, so it's going to be a really big, ugly contraption on top of the car. Not only that, because it's so unwieldy, partly because it's so unwieldy, its price is over $70,000, which is more than the cost of most cars out in the world. And this last slide is meant to illustrate a little bit of why the system is so expensive and why the optics are so complicated. And the main point is that the lenses, manufacturing lenses is challenging, and you can never really get 2 lenses the way you've designed them. There's always some kind of manufacturing tolerance that introduces error into the system. And so what you need is to align each laser diode perfectly with the receiver on the other end. But because of the lens imperfections, you don't know exactly how the alignment is going to work out until you actually build the system and test it out. So Velodyne thought of doing a laser diode, placing one laser diode on each board as shown in the middle figure here. And that would allow you to manually align each laser so that, if you see that when you're getting a received signal back, you're actually missing the detector slightly, you can slightly move the laser diode so that the beam adjusts orientation. And this is a very painstaking and expensive process because remember, there's 64 of these, and you have to repeat the process 64 times, leading to a very expensive overall system. Now, I'd like to turn it back to Mr. Jaffe to conclude our presentation. Thank you.
All right. So I'm going to speak a little bit about the two patents that we've asserted in the preliminary injunction motion. I'm just going to go through the example and the specification to talk about that design and how it works in the context of the technology that we've talked about today. Just as a little bit of background, it was filed in 2013 and issued in 2014, and this is the 922 patent that I'm speaking about right now. And then it lists the named inventors here. And then on the next slide, we have the 464 patent. And the main thing to be aware of when we're talking about the 464 patent is that it's a continuation of the 922. So the specifications between the two of them are going to be identical. So I'm going to refer to the 922 patent here, but just with the caveat that the specification of the 464 is the same. First thing we're going to look at here are a couple of the figures. And on the right-hand side is kind of what we're talking about here, which is a LiDAR. And what this is a multi-beam LiDAR. And one of the uses for this is shown on the left-hand side, which it can be mounted on the top of a car. It can be a LiDAR for use in self-driving car applications. So on the left-hand side, we have a picture of kind of what it looks like on the outside. All you can see is the housing and the lens. That's element 350 there labeled. It's kind of small to see, but we'll go into more detail in a second. So taking a step further into this, what we're going to do is on the next slide here, what I've shown is figure 2. So what figure 2 is basically what we have in figure 3, but imagine if we looked in the top of it, took off the top, and are kind of looking at an X-ray version of what's shown in figure 3. And so what I'm going to do now is walk through the different parts of figure 2 and talk about how this particular example of a LiDAR in the 922 and 464 patents works. And what I'm going to do is I'm just going to walk through the different parts of the specification in order to do that. So just talking about the basic building blocks here. What we have, and I've highlighted each part, is there are a number of different elements. So the first element that we've kind of put in a yellowish orange, I guess, is the device itself. We're talking about a LiDAR device. And I think here we can see it's all in caps, and we're still talking about LiDAR, though. Next thing to see is what's labeled as the housing. That's in blue, and that's just the circle that kind of houses the device. And then kind of getting to the inside of it, the next element that we have is marked in red, and that's called the transmit block. And as we'll see in a minute, what we're talking about here is the part of the LiDAR that transmits the lasers. That is, where we're going to shoot lasers from. What we have in green is called the receive block. So what we're talking about here are the photo detectors that I spoke about earlier. The part that's going to be able to detect the photons that come back in order to conduct that time of flight calculation I talked about before. Next, what we have the lens, which is in purple, and then the area that's labeled in gray, or marked in gray, I should say, is what's called a shared space. And in this example, why it's called a shared space is because there are photons that are being received and some photons that are being sent, both sharing, in some sense, some of the same area. So let's talk about the transmit block in particular. So what this is going to have is a plurality of light sources. What does that mean? In this example, we're talking about a plurality of lasers, for example, laser diodes. And here we have these elements that are labeled in yellow, 22A, 222A through 222C. And they're going to be arranged along a curved focal surface. Now, what does that mean? What that means is that the way that the laser diodes are arranged on this transmit board, which is a printed circuit board, in some sense, mirrors, or not mirrors, but matches the way that the lens is curved and the focal curvature of the lens. So we have, we have a plurality of light sources, and they're arranged along a curved focal surface. And here we're showing 3 transmit boards that are aimed in kind of a similar direction. So what we're going to see now is the lasers are going to shoot out, and I've marked that in red. Those are the plurality of light beams, and they're going to hit a mirror here, which is labeled 224 in purple. And what they're going to do after they hit that mirror is they're going to go through what's labeled 226, which is called an aperture. And for purposes of this example, it's a hole. And what it is, it's a hole that goes through what's labeled in 244, which we'll talk about in a bit. But it goes through that small aperture, and then it goes out into the lens, and the lens does the collimation that we were talking about earlier, which is projecting the lens and making them parallel to one another. Now,
well, just to pause on that for a minute,
Sure.
You say parallel to each other, so if they're parallel to each other, they're not going to focus on anything, and they'll always be parallel. Do you really mean parallel, or do you mean that they're going to focus on something, say, 100 feet out?
sure. So let me
What's the
clarify.
answer to that?
Yeah, so let me clarify that. So one of the important things that this LiDAR is doing is it's what's called a multi-beam LiDAR. So what we want to do is send out multiple beams to look at things. So if you look at the kind of arrows that are above what's labeled as 250, the lens, they're each going to be directed at different points out in the environment. And then they're each going to come back in different areas. And they're going to go to separate photo detectors, which are on the receive side. So instead of having, so if you can imagine it like we have, I talked about single beam LiDARs before. Imagine if I had 6, the most simple example, imagine if I had 6 of them on a table, and I were going to shoot them all out together and get responses. I would get more information about the environment by doing that.
So in your diagram, though, you have 3.
Right.
Right? And you're telling me that each of those 3 arrows is aimed at a different far field, near field, medium field, whatever you want, but it's aimed at 3 different spots.
Right.
All right. Well, okay. They can't then be parallel. They will be slightly off, wouldn't they? Just ever so slightly off.
I think that may be right. To some extent, it depends on the curvature of the lens.
I question that, but all right, it's your tutorial, so you go ahead.
Okay.
But your main point is that each of the 3 beams will hit 3 different spots somewhere out there, and they're going to bounce back. Some of the light's going to bounce back.
That's right.
All right, okay, I got that part.
So to talk about the flip side of this equation here, we're going to, as I mentioned earlier, we're going to send all this light out. Some amount of light is going to come back. It's going to come into the received lens, into the lens here that we've labeled 250 here in purple, and you can see that it's going to come back, and it's going to hit this reflective surface 242, and for our purposes, we can just treat it as a mirror here. And the photons that are going to come back through the lens, they're going to be bounced off this mirror, and they're going to go to the receive block 230, which we've labeled in yellow. What is the receive block? So it's a plurality of photo detectors. And so to just expand on the point that Your Honor was raising, it's important to understand that we were talking about the transmit boards and the laser diodes on there. And let's say just to use an overly simple example, let's say we had 6 on the transmit side. In this kind of example, a similar design, we'd have 6 individual photo detectors on the receive side, and they would map one to another. They'd be pairs. And the lens...
What do you mean pairs? You mean the transmit and receiver pairs?
Exactly.
Okay.
Yes.
But if you had, but you keep saying, you say 6, but on the diagram here we got 3, right?
Sorry,
So
I was
let's
just
stick with
making
three
a
for a
simple
minute.
example.
Each of those three on the receive side are focusing on a unique point out in the real world somewhere.
Correct.
But three different points.
Yeah, I mean, to clarify one part, I was making this example a little bit simpler by talking about 6. But just to go a little bit ahead, just to show you something. What we're looking at here is another figure from the patent. On the left-hand side, this is an example of a transmit board that we've been talking about. And on the left-hand side, what you can see is an array of these laser diodes that we've been speaking about. And so when we're talking about this diagram here in Figure 2, and in particular the elements 220, so let me see one where there's highlighted. The ones in yellow, those yellow points, if we were to pull them out and look at them, are these on the left-hand side.
Right, except you got more than three. But now on this one, this slide number looks like 61. Is that right?
That's correct.
This slide, does each one of those light emitting diodes focus on a unique point, or I think the answer is yes, but let me make sure I understand it. So on that one, you got what, 10 or 11 diodes, and each one of those would focus on some unique point separate from the others.
That's right.
Now on this example though, you got one diode, and it's you have it emitting two different beams. You see that? You got two red lines going to the lens.
Yeah, so that's just showing the kind of how it expands.
What do you mean?
So I spoke earlier about the how the light kind of expands out. This is just a diagram kind of showing how it expands out.
It wouldn't really expand that much, would it? Or
No,
does it?
You're right.
It would be a very slight. All right, but in any event, the purpose of the lens is to refocus it.
That's right.
On a unique point in the field. All right.
That's right.
Okay.
So just to rewind a little bit where we were.
By the way, I think the way you have this color-coded thing is extremely great. It's one of the best animations I've ever seen, so good for you.
All credit to Mr. Corridor on that one. So.
All right, well, he gets a A+.
So I think where I left off was we were at the receive block and talking about the plurality of detectors. And so just to rewind a little bit, we sent out some light. It went out through this aperture. It goes through the lens, comes out. We get some amount of photons that come back, and then they bounce off the mirror and go to the individual photodetectors that correspond to individual laser diodes. Now, I have a little bit more, but I'm realizing I'm running short.
Yeah, you're almost out of time.
So I wanted to.
So how do they align these things in the? If that's a trade secret, I don't want to get. But if it's in the public domain, do you sit there with a little tiny screwdriver and having somebody 75 yards away, and you know exactly what point you want to hit, and you just keep adjusting it till it hits that spot? And how do they align these things so precisely?
So what I'll say is the way that this example talks about when we're talking about the patent is the curvature of the transmit board in a sense matches the curvature on the receive side, and in that way it can help with the alignment that you're talking about.
Right. I have one other question. It has nothing really in 50 years or 10 years or 5 years, whenever the entire roadways are filled with these cars. How are they going to know? Aren't the light beams from some other car going to confuse your car? Or is there a way to distinguish between your light beam versus somebody else's light beam?
So that's actually a good question. And what we found, and what I'm not a LiDAR engineer by training, but what we found on this case is that's one of the things that Waymo has been investigating. And when they log all these miles, they've actually found some edge cases that relate to this problem and come up with some solutions to that.
All right. So, but it is a question. They're working on it. I don't think that's part of our case, but I am curious about that. Okay, why don't you've run out of time, but I'm going to give you kind of like a rebuttal and 3 or 4 minutes later if you want to comment on their presentation. But why don't you have a seat? My thanks to you both. Let's hear from the other side.
Thank you, Your Honor.
Yeah, please put it right there.
Honor, before I begin, we gave copies to the reporter, but can I bring copies to your clerk?
Sure, go ahead. And your name again?
Good morning, Your Honor. My name is Michelle Yang. I thank you. I'm from Morrison Forrester and here on behalf of defendants. And with me is my colleague, Esther Kim Chang, and she will present a portion of this presentation.
Right. Go right ahead.
I will begin the presentation with a discussion of the history of LiDAR in the context of self-driving cars. And then Ms. Kim Chang will talk about optical concepts. She'll discuss the Velodyne HDL64E sensor that's placed right here on the lectern. And she'll walk through some design and manufacturing considerations in the public domain. Your Honor asked about prior art bearing on this case. And so we will discuss some sources such as papers, dissertations, textbooks, and you have that before you in a binder. It's fairly massive, so we'll actually have the quotes on the slide. In the end, I will come back and talk about one of the design considerations, that of beam spacing, and what that has to do with LiDAR technology and the information about beam spacing in the public domain. To recap slightly, LiDAR stands for light detection and ranging, and you saw that people also use the terms LiDAR or laser radar in older references. Perhaps the best way to discuss how LiDAR works is to discuss an early application of LiDAR. One of the earliest applications of LiDAR was the use of retroreflectors placed on the moon by the Apollo missions to measure the distance between the Earth and the moon. What happened was scientists directed a laser beam at those retroreflectors. The beam bounced off those reflectors, came back to Earth, and was detected as a signal. From there, the scientists calculate the time elapsed between sending out the beam and receiving a signal. And then they use the equation, the time elapsed by the speed of light, divided by 2 for the round trip from the Earth to the moon. And that's how we know the moon is a certain distance away from the Earth.
What is that distance?
I don't know. Unfortunately, I'll find out.
186,000 miles, I think. But what is the exact number?
I have to find out, but I do know that they got in within 3 centimeters of
Really?
the distance. Yes. This is from an episode of Mythbusters, I think season 4.
All right. That's good. Go ahead.
In 1985, the Defense Advanced Research Projects Agency, DARPA, funded the Autonomous Land Vehicle Project. And you saw previously a photo of the NAV lab. So Carnegie Mellon University's Robotics Institute funded, with DARPA money, the Navigation Laboratory Project. And the first NAV lab, the NAV Lab 1, was a van that was computer controlled, so no human behind the wheel, using a laser rangefinder from the Environmental Research Institute in Michigan, the ARIM laser. That rangefinder here is marked in a giant red box, so that's the size of the rangefinder. The ARIM laser used two mirrors to direct the beam in a 80-degree horizontal field of view and a 30-degree vertical field of view. And as shown on the next slide, what was needed was to measure the time of flight, calculate the time elapsed between sending the beam and receiving a signal. And from there, they could calculate the distance of objects in front of the NavLab vehicle. Through the rack of computers shown here, in this diagram, back then the rack of computers was 639 centimeters wide, an entire stack of them, they could calculate the data and produce a 64 by 256 pixel image. That was advanced technology for 1985. By the 2000s, DARPA used congressional money from public funding to provide $1 million prizes for the DARPA Grand Challenge. And you heard about the 2004 and 2005 races. Well, in 2007, it was the DARPA Urban Grand Challenge. It was a closed course, 60 miles on an Air Force base. Unlike the previous DARPA Grand Challenges, the self-driving cars there had to navigate traffic rules, and avoid bumping into each other. The winner of the 2007 DARPA Grand Challenge was Carnegie Mellon University and General Motors car, the Boss. And on top of that Boss car was a Velodyne sensor, a 360-degree spinning LiDAR with 64 laser beams. I do want to note that one of the entrants in the 2004 and 2005 DARPA challenge was the Ghost Rider. It took me a moment to realize this, but it's called the Ghost Rider because there's no rider on the actual car, on the actual motorcycle. This Ghost Rider did not use LiDAR. It used two forward-facing stereo cameras. In the back, folded up, are two arms that could right the motorcycle when it toppled over. And the Ghost Rider was the only two-wheeled entrant to make it to the semifinals of the 2005 Grand Challenge. Today, it is in the Smithsonian, and it was created by a team from the University of California, Berkeley, led by Anthony Lewandowski. In the modern self-driving car, a variety of sensing options are used. Marked in red here is a 360-degree spinning LiDAR. But there are also front-facing cameras, rear and side cameras, radar coverage, as well as an inertial measurement unit, because the car is being jolted. So the IMU measures the pitch and adjusts the data to account for this shaking and jolting. And of course, you need significant computer and data storage capabilities to handle processing all this data. And with that, I pass the presentation on to my colleague.
Okay, I may be wrong about the 186. I think that's the speed of light.
That's good, yeah.
So, one of you will give me the right answer about the moon, but
I'll go back and watch
right.
Mythbusters.
You'll get that from me. Thank
Absolutely.
you.
Thank you.
Good morning, Your Honor.
So your name again?
Esther Kim Chang.
Perfect, thank you.
I'd like to begin by explaining some optical concepts as applied to LiDAR applications. To recap briefly how a LiDAR system works, I'd like to use an illustration from the Field Guide to LiDAR. This field guide was authored by Dr. Paul McManaman, who is our expert in this case. This diagram from the field guide demonstrates the basic idea behind a LiDAR system. Pulses of laser light are emitted from a light source. They go out into the world, hit a target, reflect off of that target, and come back to detectors in the receiver on the LiDAR sensor. An actual LiDAR sensor will use multiple laser beams, but for simplicity's sake, what we did was shaded all the outgoing light in red and all the incoming light in blue. LiDAR systems can be categorized as either monostatic or bistatic. A monostatic LiDAR system uses one lens for both the outgoing transmit beam as well as the incoming receive beam. Monostatic systems were described in a publicly available reference on laser radar from the National Academy of Sciences. Incidentally, our expert, Dr. Paul McManaman, chaired the committee that was responsible for this publication. Here, I've taken an illustration from this reference to illustrate how a monostatic system works. You have light from the laser light source going out into the world, hitting a target. The light reflects off of the target, and the reflected light comes back to the sensor through the same lens that was used to send the light out. In the bottom right corner of your screen, you'll see a picture of the AGM-129A cruise missile. That's an advanced cruise missile, and in 1983, General Dynamics got a contract to develop this missile. It's a stealth nuclear-capable missile that was used by U.S. Air Force B-52 bombers, and it's one of the earliest examples of a monostatic LiDAR system. Another more recent...
What did it do? What was it trying to detect?
I think targets to hit, Your Honor. It's a missile. Another more recent example of a monostatic LiDAR system is disclosed in the 922 and 464 patents, which are two of the patents that are asserted in this case. As explained by Waymo's counsel, these patents describe a monostatic LiDAR system because the outbound transmit light and the inbound receive light go through the same lens. As shown in Waymo's slide 54, you can see that the red laser beams that are being transmitted from the diodes go through the lens that's labeled 250 and shaded in pink and go out into the world. The light hits on objects in the world, gets reflected back, and as shown in slide 56 of Waymo's presentation, 56, the light comes back through the exact same lens labeled 250 and shaded pink. So this is a monostatic LiDAR system. The other type, going back to our presentation, the other type of LiDAR system is the bistatic LiDAR system. In contrast to a monostatic LiDAR system, which uses one lens for the outgoing transmit beam and the same lens for the incoming receive beam, a bistatic LiDAR system uses a separate lens for the transmit beam and the incoming receive beam. Here, I've taken an illustration from the Field Guide to LiDAR that was authored by Dr. Paul McManaman. And as Mr. Jaffe indicated earlier, TX is often used as an abbreviation for transmit, and RX indicates receive. So in this illustration, this indicates a bistatic system. You can see with the red arrow that I've drawn here that the light goes through the TX or transmit lens out into the world, hits the target, and the reflected light comes back and comes through another separate lens, the receive lens, back to the LiDAR sensor, and then to the detector where that reflected light is analyzed. One example of a bistatic system is the Velodyne HDL64E. You have a picture of that in the lower right corner of your screen. I'll go into more detail on the Velodyne sensor shortly, but for now, I want to point out a couple of features of the Velodyne sensor.
That's what's up there?
Yes, sir.
That's the same unit?
Yes, Your Honor. You'll see that the Velodyne sensor has two optical cavities, one on top, one on bottom. Each optical cavity has three lenses. There are two transmit lenses on either side and one receive lens in the center. It's a little bit hard to tell from this picture, but the two transmit lenses are smaller than the receive lens. And that's because when the light goes out into the world and deflects off of objects, the light becomes scattered and dispersed. So having a larger receive lens helps collect more of the reflected light.
Receive is on the top?
No, so actually these are two units that are similar to one another. You have the two transmit lenses on either side and the top, and the receive lens in the center of the top cavity, and you have the same setup in the bottom. Two transmit lenses on either side and one receive lens on the bottom. the way the HDL64E is set up is that you have a total of 64 laser diodes, but 32 of them are contained in the top cavity and 32 are contained in the lower cavity. And there's a tilt of the two optical cavities to allow for detecting items in different distances. The optical cavity in the bottom is tilted downward to be able to detect things that are closer to the sensor.
I got that part, but you said that the receive lens was larger, and I understand your logic.
So,
But that's only true on the bottom one, on your.
I think in the picture it's harder to tell because of the downward angle of the lower optical cavity. If you look here, you can see that this receive lens here is bigger than the two transmit lenses on either side.
All right. I take your word for it. I can't tell from
sorry.
that, but your diagram makes them look
The
looks
picture
the same.
is misleading. I blame our photographer.
Okay, but on the bottom one, it's clearly the receive is larger than those two red ones.
Yep.
All right, I
think
get.
if you maybe after the tutorial, if you want to come take a look at the device, it's hard to tell from where you're sitting, but the two transmit lenses on either side are smaller than.
How heavy is that thing? You can hand it up to me, or is it heavy?
May I approach?
No, is it heavy? I don't
it's
want.
33 pounds. It's not too bad.
All right, bring it. Why don't you just walk it up here? For
Okay,
a second.
sure.
Put it right here. Okay, here you can take it back. Unless there's more that I need to look at. I can't really tell, but oops, you all right? All right. I take your word that it is larger. It's hard to tell because of the cabinet there.
Yep.
The housing.
So this is to point out that the Velodyne sensor is a bistatic system because it has separate lenses for transmit, which are the two lenses outlined in red, and another lens for the receive. And that's multiplied twice in the top optical cavity and the lower optical cavity. So there are 4 transmit lenses, 2 receive lenses in the Velodyne sensor.
How long has the Velodyne sensor been available?
Since 2007. So the founders of Velodyne were David Hall and Bruce Hall, 2 brothers. They founded a company called Velodyne in 1983, and it started as an audio company, an acoustics company, and they specialized in low-frequency sound and subwoofer technology. But then in 2005, you heard about the DARPA Grand Challenge. They decided to enter that competition.
Kind of like the Wright brothers.
Yes. And as part of that competition, they developed a LiDAR-based system that laid the groundwork for the current LiDAR products that Velodyne is selling today. And by 2007, 2 years after they initially entered the competition, 5 of the 6 vehicles that finished the 2007 DARPA Challenge were using the Velodyne HDL64 sensor.
Does that unit, in addition to having the light emitting diodes and the lenses and the cavities, does it actually have the computer and the software built into it to evaluate what the return signals are?
Yes, John. So there's a circuit board on top that processes all of the information, and then there's an Ethernet cable that sends all of the information to a computer.
A special computer, or would one of our computers here in the courtroom work?
I'll have to, I don't know. I would have to confirm that information and get back to you.
It would be kind of nifty if we could hook it up right now and get my computer to show the courtroom. That would be.
Your Honor, yesterday I was at 737 Harrison, and from the sidewalk you can see auto trucks with Velodyne sensors spinning. So if you're interested, you could take a walk down to Harrison and Fed and see that for yourself.
Oh, maybe I will. All right. Okay, continue on, please.
You may ask, one thing I wanted to know is we discussed the 9 922 and the 464 patents and how it describes a monostatic LiDAR system, I wanted to note that the 922 and 464 patents do not cover a bistatic system. They only disclose a monostatic LiDAR system. You may ask...
I don't want to get too far into this part, but on those patents, is the claimed invention one lens? You're making it sound like one lens was already known all the way back to the cruise missile.
Well, Your Honor,
what is it that they must be more than that? It must be one lens plus something else.
There is more, but may I state what Waymo has stated in their papers?
Yes.
Okay, so they tout the single lens innovation of the 464 and 922 patents, and they talk about how groundbreaking the single lens design was. Obviously, we disagree with that allegation because we see monostatic systems in the prior art, and we're talking about some of them today.
Okay. All right. We'll have a lot more on that later on, but okay, thank you for that. Please go ahead.
So you may ask, why choose one type of system over another? Well, each system has disadvantages and advantages. In a monostatic system, you're dealing with one lens for both the transmit and receive beams. Because you only have one lens, it's more compact, it's lighter, but you have this issue with getting some backscatter because you're using the same lens. On the other hand, with a bistatic system, you don't have that interference issue because the lenses are separated, but then you have to be really careful about aligning the two lenses so that the angular relationship between the emitters and the transmit lens is the same as the detectors and the receive lens, because that's the only way that the detectors will be able to pick up the reflected light from the emitting diodes. So we've talked a little bit about the Velodyne HDL64E, and that's the product or the device that I've brought to court today. As I mentioned earlier, Velodyne is a Silicon Valley company based nearby in Morgan Hill. And we discussed how by 2007, 5 of the 6 vehicles that completed the DARPA Grand Challenge used the Velodyne. And today, it's the most widely used commercially available LiDAR sensor in the market. And it's been used by many companies, including the parties to this litigation.
What other self-driving companies are using it?
I would say, I don't have an accurate inventory, but I would say the majority of companies have or are using the Velodyne sensor. There are other LiDAR sensors, but by far the Velodyne HDL sensors are the most popular.
I read in one of these things, Tesla doesn't use LiDAR at all.
At all, yes, yeah. That's correct, Your Honor. So I think both parties have mentioned that there are a lot of different sensor technologies like radar, cameras, and there are pros and cons of all of the technologies. Some people think that LiDAR-based technology, while it is popular in the short term, will be replaced by better camera technology and other sensor technologies down the road. The Velodyne HDL64E is a 360-degree LiDAR. You can see it's spinning here. And what it does...
Oh, how fast does it spin?
So the Velodyne sensor can go from 5 hertz, which is 300 revolutions per minute, up to 15 hertz, which is 900 revolutions per minute. Human reaction time to step on the brakes in response to an object or an event is 5 hertz per second, is 5 hertz or 300 revolutions per minute. So the Velodyne sensor is at least as good as human reaction time.
Wait a minute. So in 1 second it goes around how many times?
300. Oh, sorry, 1 minute.
In 1 minute it goes around 300.
Yes, Your Honor.
So that would be, what, 5 in a second? 5 times per second.
Yes.
So, all right, so that's kind of a herky-jerky image, isn't it? You know, because the old movies used to be, you know, even faster than 5 frames per second. But I guess what you're saying is that, all right, the refresh rate is what you're talking about.
Yes,
Refresh
well,
is
it's going
5
around
times,
300 times. So during that
but
time,
in a minute, by 5 times in a second.
yes, Your Honor.
All right. So, but how fast can a car go in a fifth of a second? I don't know. What's the answer to that?
Well,
If
so
somebody's
my
going 60 miles an
understanding
hour.
is-
I'm just curious. If you go 60 miles an hour, let's work this out. How many feet per second is that?
Your Honor,
I used to know the answer to that.
60 miles an hour,
Uh-huh.
1 mile a minute, that's 88 feet per second.
Right. So 88 divided by 5. About, what is that? About
17.
17. So between each spin, it goes 17 feet. You could be going 17 feet before you get a refresh.
My understanding is
safe? I
that
don't know. That's something. A lot of things could happen in that length of time.
the current LiDAR devices are limited to a range of 35 miles per hour because if you go faster than that, you outpace the LiDAR
I
sensor.
say, all right. So that helps. That reduces the problem a lot. Okay.
So that's why the parties and other companies that are working in this space have different types of LiDARs. They have medium-range LiDARs, long-range LiDARs. So I believe the HDL64E goes up to 120 meters, if I'm remembering the product spec correctly. So definitely the LiDAR sensors are intended to only have a certain range.
What is on this particular unit here? You have one that looks down, right, the near field, and we have one that looks, what do you call it, the far
Out.
field, the medium field? What do you call it?
So you can call it long range.
Right, you got the long one, but the other one is what? Short range or medium
Short range.
Right.
It depends.
But
I would probably say medium range. And
all right, so let's
long
say
range.
medium, whatever you want to call it. But when it's on top of a car, what are the zones that are being imaged as you?
My understanding is that medium range LiDARs typically cover up to 30 meters, and the long range further out. But I may be misremembering facts.
All right.
But I do know that a lot of cars use different types of sensors. So Velodyne also has short range sensors, and a lot of people will combine sensors or camera technologies to get objects closer to the car.
Oh, on this particular one we have right here, what is the closest it will image?
I don't know, Your Honor.
Okay. It's all right.
I can get back to you.
We can learn that. All right. Okay. You got about 15 more minutes total.
Okay, I will talk very quickly. We're going to skip some videos that I had, but I do want to show you the end product of a LiDAR sensor. On the left, this is actually taken from a video featuring Velodyne co-founder Bruce Hall, and he used the Velodyne sensor to image a parking lot. On the left, you see a picture of the parking lot. On the right, you see the point cloud that was generated using the Velodyne sensor. The Velodyne sensor will take data at about 2.2 million points per second and generate an image or 3D map of the car's environment, and that 3D map is referred to as a point cloud. We've talked about how a LiDAR sensor works, and we've discussed the Velodyne sensor. I want to turn now to a discussion of some of the design and manufacturing considerations that come into play when designing a LiDAR sensor, and how those considerations have been addressed by literature in the public domain. As I noted, in the Velodyne LiDAR sensor, you have one laser diode per printed circuit board. But that's not the only way that you can do it. In the Velodyne sensor, you have 32 printed circuit boards on top, each circuit board having one diode. On the bottom, you have 32 printed circuit boards, each circuit board having one diode. But as a 2015 textbook discussed, you don't have to have just one diode on one substrate. You can have multiple diodes on a substrate, and in fact, you can have multiple substrates with multiple diodes. This textbook describes a laser stack with 3 substrates each having 10 laser diodes. When you have multiple substrates or printed circuit boards, there's an issue that arises, and that issue is how do you align the circuit boards? It's really important for a LiDAR sensor to have accurately aligned printed circuit boards, and there's a lot of manufacturing tolerance that affects the manufacturer of printed circuit boards. So you have to figure out a way to accurately align the circuit board so that the laser diodes are also accurately aligned. The concept of using guide holes to help with the alignment of printed circuit boards is something that has been known to the public since at least the 1970s. For example, in this patent that was filed in 1976 and assigned to a company called Pertec Computer, it describes the use of two holes outlined in red on the right in figure 1 to assure alignment of the PCB or printed circuit board.
What did that printed circuit board do?
What did this circuit board do?
Was that a diode light emitting thing or something else?
I believe these were laser diodes, but I can double check that for you, Your Honor. This reference is also included in your reference binder. And on the right, it indicates the use of the guide holes to align the printed circuit board to another structure. And the way those guide holes are used is that pins outlined in green in figure 3 are inserted through the guide holes. And on the left in figure 2, you see a cross-sectional view of the pins being in the guide holes. And that was how this patent disclosed aligning printed circuit board to a structure. There is another alignment issue that comes up when you're dealing with printed circuit boards and diodes, and that's how do you position components on the circuit board, including diodes, when you are manufacturing these boards. To solve this problem, it was well known that you could also use holes as a reference point to position internal components. So here, in this patent that was filed in 1981 and assigned to Siemens, it describes location holes 7 and 8, outlined in red, and those location holes are used as a reference point for position determination of components on the printed circuit board. So those holes, 7 and 8, are used as a reference point to get the XY coordinates of other components that you want to place on the reference board. So we've talked about holes to align printed circuit boards to each other or to another structure, and we've also talked about using holes to position components on the circuit board. But holes are not the only way that you can use to position components on the circuit board. Another way is to use something called fiducial marks. This is a diagram I pulled from the website from a PCB manufacturer, and it discusses the use of fiducial marks to align components on the board. The fiducial marks are the red marks, which are called out by the yellow arrows. And these marks are used as reference locations so that you can measure X and Y positions of other components relative to the fiducial. Let's take a I am going to skip my next slide because I see I'm running short on time. And I want to talk about one last issue before I turn it back over to Ms. Yang. So we've talked about using holes or fiducials to position the diode on the PCB. That tells you how to position a diode on the circuit board, but it doesn't answer the question of what is the best position for a diode. An issue that often arises when you're trying to position a diode on the circuit board is how much of the diode should lie on top of the substrate. In a 2015 textbook, it describes the issue of how much of the diode should be positioned on the substrate. And it talks about the consequences of each scenario. In an ideal world, you will want the laser diode, which is illustrated by the black box in this diagram, you will want it to be flush with the substrate. In our scenario, it would generally be a printed circuit board. But due to manufacturing tolerances, you can't always get it to be flush. So you have two choices. You can either push it out a bit, causing the laser diode to overhang the edge of the substrate, or you can push it in a little bit to make sure that the entire diode is laying on top of the substrate. The 2015 textbook discusses two considerations that come into play in terms of the benefits or disadvantages of having an overhanging diode versus an underhanging diode. One thing to keep in mind is heat dissipation. Laser diodes generate a lot of heat, and the main way that they get rid of the heat is through conduction. So the more of the laser diode that you have sitting on the substrate, the better heat dissipation that you have. But the competing concern is that when these laser diodes emit light, if you have it pushed back too far, the laser beam gets obstructed by the edge of the substrate. So considerations relating to the overhanging or underhanging of diodes was something that was known in the public domain. And even as far back as 2007, in a dissertation that was publicly available, it discusses the benefits of overhanging the laser diode over the edge of a substrate. Here the laser diode is labeled laser bar, and the substrate is labeled heatsink. And it discusses the benefits of overhanging the diode because it limits the obstruction of the emitting light. As you can see, the advantages and disadvantages of diode overhang and underhang were well known and out in the public domain. At this time, I'd like to turn it back over to my colleague, Ms. Yang.
All right, thank you.
Your Honor, I know we're a bit short on time, so let's talk about a question you asked, which is, what happens when you're driving a car at speed? If you're driving at 30 miles per hour, for example, you're traveling 44 feet every second, which means you want to see more than 44 feet in front because you want to have time to react, to brake or turn your car. The laser patterns that come out of a LiDAR sensor have a formation we call this beam spacing, which refers to how you allocate or you space out the beams in a given vertical field of view. As you can see here, the beams that are tilted downwards will hit the ground or closer obstructions and be bounced back very quickly. But it's the beams that go the farthest into the horizon, which we call the level horizon as 0 degrees forward. It is those beams that will go and show you the object in the distance. For example, the lady on the right-hand side of the slide. However, you may notice that as beams travel farther from the LiDAR, the space between them becomes farther apart. And as is shown in this simplified illustration, the beams will not hit the shorter cone next to the lady at around knee height. And that's a problem, having gaps in the beams that go furthest into the horizon. One group of engineers tried to solve this problem by looking to nature. Here's a paper published in 2015 from some folks at HRO Laboratories in Malibu, California. And they said, we address this issue by looking to nature and to create a higher density foveated region. So I was a biology major, and foveated vision refers to something inherent in our eyes. In the back of your eye, there's indentation where the retina thins out slightly and the cones there are in their highest concentration. That means that the cones there receive the most light and see with the greatest visual acuity. In other words, you have higher resolution visually at the center of your vision and lower resolution at the periphery. Foveated vision is inherent to our eyes. These engineers at HRO Laboratory try to replicate foveated vision using two LiDARs. What they did was balance one of the 32-channel Baladine LiDARs, which means one of those gray barrels, on top of the other to create a double density pattern. And let me show you how that worked. The first Valadyne sensor, 32 beams, illustrated here in simplified form, sends out a pattern. And as you see into the distance, there's a gap between the lasers that go furthest towards the horizon.
I don't understand. What do you mean gap?
If you look at the human, so on the left-hand side, when the beams are emitted from a center point, they're very close together. By the time they reach the human, there's a gap. For example, one beam might hit his shoulder, and the next beam will go towards halfway down his arm.
I mean, as you get farther away, the
Yes.
beams are, the gap is larger.
That's right.
Okay, I see that point. All right.
Okay. I had a Lego diorama I was hoping to bring out for this moment, but I think we're short on time.
No, go. I want you to finish this point.
Okay.
You're talking about the strategy of how you do the beams.
To
Yeah.
eliminate the gaps.
So let's hear your point. Go ahead.
What they did was they balanced a second LiDAR on top of it to send out 32 beams as well. In these experimenters, they balanced two LiDARs together so that there was an overlap region. And where there was a gap before, now there's a denser concentration of the laser beams. And what they cared about was what they called the fovea, the center region, which is where the person is standing here. And because that is a region furthest in the distance into the horizon. And you want to see objects in the distance when you're driving at speed. Your Honor, if I may move. Oh, please.
You said your title there says greater resolution needed for farther distances.
Yeah, for objects at further distances.
But I mean, I'm asking.
Mm-hmm.
It seems to me that if something farther away, you're less likely to hit it than something that's real close. So why couldn't you make the argument that it's more important to have more beams in the near field than the far field?
The reason is because the beams in the near field, if you have downward tilted beams, they hit the object and come back very quickly. Whereas the beams further afield, the light goes out, comes back, and in the meantime, your car is moving forward. And that's why you'll be arriving at the lady in the distance very quickly, 44 feet per second. And also,
but we're talking about the speed of light. It's so fast. I have to think about that. All right.
Okay. I think the point is vertical resolution is about the density of the angles. So having narrower angles between the beams to eliminate gaps between the beams. And so to cover objects of a certain size.
All right, so what was the source, the public domain reference that discussed the strategy for how you align your beams? What was that again?
For how to align the beams, this paper is a 2015 paper.
The one about the eye, they said they were going to follow what nature does.
Yes, that's this paper, 2015 paper from the HRL laboratories. And so I'm quoting, previously they say we address this by looking to nature. That's on page 2. And then we go back and here's an image from page 1 of how they did it. And here's a figure from the same paper. And I just want to close by talking about this strategy was applied using two LiDARs, one balanced on top of each other. But
this one right here.
yes,
The one
sort of like this one. The Valadyne, the folks who made that LiDAR, they actually talked about how you can do it within one cavity. Here's the 190 patent. It was filed in 2006, issued in 2014. There they talked about having a fan pattern of stacks, PCBs, with one emitter per PCB. However, they say within just that one cavity, you can create an intentionally variable density in your emitters. You can create the higher density at desired regions. And they close by saying some uses require increased density, which is desirable to facilitate seeing further objects at further distances and with more vertical resolution. And today, in the Velodyne LiDAR, what they do is they have two separate cavities. The one on top is aimed towards the horizon. And you notice in the spec sheet here from the Velodyne website that the emitters are more tightly packed together, so that the beams that go for the horizon are more densely grouped. In contrast, the beams that are in the lower cavity, which are pointing downwards to see objects closer to you, they're more spaced more far apart. And that's in the spec sheet on their website. In closing, I just want to provide a bit of context in terms of timeline, where here above we have early autonomous vehicles going through the DARPA challenge to today. And we note that the Velodyne LiDAR you have before you was introduced in 2006 and 2007. Below, I just note that the manufacturing and design considerations you saw just now for individual components in LiDAR were introduced, well-known, and in the public domain in the earlier periods leading up to before 2015. And with that, I conclude my presentation. Thank you very much.
All right, you two did a great job too. Thank you. All right, rebuttal. I'll give you a few minutes for rebuttal if you would like to use that.
Thank you, Your Honor. Just a couple brief points. Your Honor raised some discussion of the 922 and the 464 patents and kind of what is that design versus the monostatic designs that they talked about before. And I just wanted to be responsive to that point. So there's a couple things to be aware of. Number one is we're talking about the use of a single lens in the example in the specification, and then a plurality of laser diodes. And so there are all sorts of complications that come up when you use multiple lasers and a single lens. So that's just one of the reasons why the design that's described in those patents are different from the designs that they were talking about.
So you're saying that the first time anyone ever used more than one diode with a single lens for transmit and receive was in your patent?
I think I don't want to recite all the claim limitations right here, but I think generally that's the idea.
Really? Okay. All right, great.
And then the other thing I just wanted to mention is we talked a little bit about the Velodyne and the pluses and minuses. I wanted to give a little bit more context for the court on how what's described in the 922 and 464 patents relates or compares to what's described right here. And just for the court's benefit, so what we're looking at there is about 28 pounds, and again, I think, as Mr. Corridor mentioned, it's about $70,000 at one time, whereas what's described in the 922 and 464 patents, it's about this big, and you can, I don't know, it's probably 5 to 10 pounds at most, and so there's all sorts of manufacturing benefits that flow from these designs that are not present in this design right here, and that actually leads to lower costs as well.
Great, thank you. I think both sides did a fantastic job. I learned a lot. We're going to take a short recess, and then we're going to come back and hear your discovery disputes in, say, 10 minutes. All right, thank you.